Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list published on February 20th, 2026, just 4 days ago. It introduces a framework called EgoPush, which enables mobile robots to rearrange complex objects using only their own camera view, achieving an 80% success rate in the real world without relying on global maps. The paper is titled EgoPush, Learning End-to-End Egocentric Multi-Object Rearrangement for Mobile Robots. And as we'll see later, the specific way they constrain the teacher model during training has massive implications for how robots learn to navigate dynamic environments. Figure 1 illustrates the core task. On the left, a Turtlebot 3 robot operates in a real-world arena, tasked with arranging colored boxes into a specific cross configuration using only its onboard camera. The middle column captures the physical execution, showing the robot successfully pushing blocks into the target shape. Then, the right panel visualizes the student policy in simulation, tracking the robot's trajectory as it navigates obstacles and forms other patterns, like lines, demonstrating that the learned behaviors transfer effectively between simulated and physical environments. Figure 2 details the full EgoPush framework, which splits learning into 2 distinct phases to bridge the gap between simulation and reality. The top row illustrates phase 1, where a privileged teacher policy trains on exact 3D key points rather than raw pixels. Crucially, look at the green panel on the right. The teacher's vision is restricted to the robot's actual field of view, preventing it from relying on information a real camera wouldn't see. Moving to the bottom row, phase 2 introduces the student policy. It uses depth maps and semantic grouping to estimate the teacher's latent states, effectively learning to mimic the expert behavior using only noisy visual data, which enables the successful real-world deployment seen in the final photograph. Well, figure 3 demonstrates why those teacher constraints are necessary. In panel A, the proposed EgoPush teacher is forced to look at objects to track them. You can see the robot orienting itself, so the blocks, marked with yellow key points, stay inside the cyan lines representing its camera view. Contrast that with panel C on the right, which shows a teacher with global knowledge. Because it knows where everything is automatically, it drives away without looking back, creating behavior a real robot simply cannot copy. So, Table 1 quantifies the impact of these observation strategies on actual performance. In the teacher columns on the left, all 3 variants perform brilliantly, with success rates exceeding 98%. The global teacher in the bottom row is actually the most efficient, showing the shortest trajectory lengths. But the student columns on the right reveal the catch. That global teacher produces a student with a 0% success rate, completely failing to transfer its skills. Meanwhile, the EgoPush student in the top row achieves about 71% success, confirming that a teacher must share the student's limitations to be effective. Alright, moving to the reward structure, Table 2 breaks down the impact of credit assignment, which determines how the robot learns which actions actually led to success. The first row, labeled Base, shows that providing a reward only at the very end of the task fails, yielding a meager 16% success rate. By contrast, the second row shows that adding stage-wise rewards, or SWR, creates a massive jump to 88% by providing feedback on sub-goals. Finally, the bottom row demonstrates that adding a stage resetting timer further refines this signal, pushing the success rate to nearly 99%. Now, Table 3 compares EgoPush against standard baselines on a simplified version of the task. The classical approach, labeled Sim in the top section, manages about a 19% success rate, but it struggles because position errors accumulate over time. The middle section lists various end-to-end reinforcement learning methods, including those with depth and memory. Surprisingly, their success rates collapse to near 0%, confirming that standard RL simply cannot handle the partial visibility involved. In stark contrast, the bottom row shows EgoPush achieving a perfect 100% success rate, proving that the structured teacher-student distillation is critical for solving these long-horizon problems. Wrapping up, EgoPush shows that to build robust robots, we must train teachers that respect the student's limitations. By constraining the privileged teacher to the robot's own field of view, the system learns active perception strategies that transfer seamlessly from simulation to physical reality. This shift allows mobile robots to perform complex, long-horizon rearrangement tasks without relying on brittle, global maps. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.